Let's look into how we can apply the Boolean algebra in simplifying Boolean expression. Let's take this first example. The first thing that we have to do is to look for common literals. And on this example, we can see that there are no common literals. However, in rule number 10 of Boolean algebra, we have there what we call the A plus AB is the same as A. So we can use this as substitute for this term to expand this expression. So we get A plus AB plus the remaining term, not A, times B. And then we can factor this by removing the common terms between these terms, and that is B. So B will be out of the bracket, and what is inside are just the A and the not A. Then we copy the remaining term, A plus B. And then we work on this, so this gives us 1 times B plus A. And B times 1 is always B. So it gives us A plus B. So this turns out that this expression is the same as A plus B. We can plot a truth table so we can verify our answer if it is correct or not. So let's write here A and B, A plus not AB. So let's write here the number of combinations for our input. And for A, if it is 0 and not A, we negate the values of this. And for B, let's just copy everything. And then let's try to operate for the final result. Anything that is multiplied by 0 is always 0. So this is 0, 0, and 0, we get 0. 1 plus 0, we get 1. 0 plus 1, we get 1. And then 0 plus 1, we get 1. So this is same with A plus B. If we will just add A to B, we'll get the same column for our F, which is the final result. So let's check. A plus B, 0 plus 0, we get 0. 0 plus 1, we get 1. 1 plus 0, we get 1. And 1 plus 1, we get 1. So you can notice that we have same column values for F and for A plus B, which concludes that A plus B is the same as A plus A, or not A, times B. Now let's look how we can draw the logic circuit for non-simplified expression and for the simplified expression. This is the non-simplified and this is the simplified expression. So we have the AND here. Let's start with the AND. So it states here not A times B. So we get, so this is the AND gate. And then we have B here. And then we have the NOT symbol. And this is our A. Or our NOT A times B. So we have already drawn the truth table for this. Now let's add the last term. So this becomes OR gate since we have the addition sign. And right here A. So this is now the complete logic circuit for this non-simplified expression. Now let's write the logic circuit for the simplified expression. And let's identify the difference between these two logic circuits. So we have only one operator, that is the OR. So we write here, and then the input A and B. So comparing the two logic circuits, it seems that the non-simplified has more operations in it, while the simplified has only one operator. So to sum up, what we have on this logic circuit is that logic circuits with numerous operators tends to be slow when it comes to processing. However, for simplified, since there are only few operations involved, it will be easier for a computer to process the logic circuits. And the same applies for truth tables and Boolean expressions. This time, let's take another example for simplifying Boolean expression using Boolean algebra. So let's look for the similar terms, and for this case we cannot find, but however, we can actually expand this term, just like what we did on the first example. So if you can still remember, we have a rule in Boolean algebra that A plus AB is the same as A, and we can use that to expand this term. So we will get A plus AB plus the remaining terms. Then we get not A times B plus not B. And then we can work on this. So we will get A plus the common term is B, so we will put that outside the parentheses. And what is left inside are just A plus not A, then plus not B. And then this turns out to become 1. So B times 1 plus A plus not B. So this becomes B plus A and then plus not B. So B plus not B, this becomes 1. And then A plus 1 is just 1. So this is our answer. So we can say that whatever the value for A and B, either 0 or 1, the result will always become 1 as far as this is the given expression. Okay, we can check this out by using a truth table. So let's write here A and B, and then let's write here A plus A, or not A times B plus not B. Then for our final result, we will write there the output. Okay, let's say we have 0 for our A and 0, 1, 0, 1 for our B to complete the combination. And then this is our A. We will just copy the column A. For not A, we will just negate the values of A, then negate the values for B. So looking at this is an AND. So whenever we see 0, automatically that gives us a 0. So 0 plus 1 plus 0, this gives us 1. 1 plus 0 plus 0, this gives us 1. 0 plus 1, this gives us 1. And this is also 1. So no matter what value we give for our A and B, as far as the given expression is this one, so the result is always 1, which is very much evident to what we had on our simplification. Okay, so now let's try to write the logic circuit for this problem. For the unsimplified, let's start writing the logic circuit for this term. So we get B and then the NOT gate. Okay, then let's work on this. So we have an AND, the other side is B, and then the other side is a negated a. And then the last part is the a. So we will just write here. So this is the or. We are now adding not a times b plus not b. And then we have to do another or for our a. Okay, so this is not the complete logic circuit for the non-simplified expression. For the simplified one, we can only write 1 and so that's the way how to do it. So as you can see, there is no operations involved in the simplified version compared to our non-simplified wherein there are so many operations involved. Okay, so let's answer this problem as our third example. So the first thing that we have to do is to look for the common terms, and we see that the not A is the same as with the not A for the second term, as well as the C and the C. So we can perform factorization, and C times not B less B. And then we can also do the same thing for this term because we can see that C is common for both of these. So we can state here not C times B plus not B. So not B plus B. So we can state here that B, if it is 0, having B and not B, adding them together. So this gives us 1, this gives us 0, this always results to 1. If it is 1, this becomes 0, and this is 1, this always results to 1. So this means that this expression here is always 1, as well as on this expression. So what we get is just A C times 1 plus not C times 1. And C times 1, if C is 0, and then C times 1, this is 0. If C is 1, and 1 times 1, this is 1. So meaning the result is very dependent on C. So therefore, the answer to this one is just C. And same goes with this. This is just not C. Then on this part, we can apply absorption property. So just like the rules for our Boolean algebra, we have there the A plus not A, B is equals to just A plus B. So this becomes A plus not C. But if you want to expand this expression here, so we can state that C plus C not A plus A not C. So this is the C and the AC. Okay. So we're gonna work on this part. So C plus, we can put the common outside of the bracket, and that is the not A. And what is left inside are just not C and C. And if you can still remember, this is almost the same as this, which gives us a result of 1. So this becomes C plus not A times 1. And the final answer would be not C plus A. So this is it, not C plus A. or not A plus C. Let's now look into the truth table of the simplified version and the non-simplified version of this problem. Okay, so it's quite big for the non-simplified. However, for the simplified one, we have only three operations. As for the non-simplified, we have big numbers of operations, which is very tedious to write it down manually. Okay, so let's write down here our truth table. Let's write the ABC here. So we have to indicate the number of cases for this truth table. So basically we have 0 and 1. So we have 2, that is the 0 and 1. And we have 3 variables, so we write here 3. So this gives us, which is a total of 8 cases. So since we have 8 cases, we have to separate the 4 zeros and 4 1, which is a total of 8. And then we have to alternate 2 zeros and 1s, and we have to alternate 1 0 and 1. Okay, so this is a bit tedious, but we have to deal with it because this is how the way to validate our answer if it's correct or incorrect. So for our A, we have to negate all the values of A. So this becomes 1, 1, 1, 1, and 0, 0, 0, 0. Same with B. This is 1, 1, 0, 0, 1, 1, and 0, 0. For C, we will just copy everything. And for A, this is 1, 1, and then 4 zeros. For B, we have 2 zeros, 2 ones, alternating from time to time. And then for C, there's an alternate of 1 and 0. For B, another alternation of 2 zeros and 2 ones. And then for C, starts with 1 because it is negated. And then for B, starts also with 1 because it is negated. And for C, we also starts at 1. Okay, this is our final column. Okay, so let's look into this. So this gives us 0, and this and here gives us 0 also. This is also 0, and this is 1. So we get an answer of 1. This is 1, so automatically we get a result of 1. This is 0, 0. Okay, so this is 1. So we get an answer of 1. This is 0, but this is 1. Let's write 1 here. This is 1, so we get an answer of 1. This is 0, 0, 0, but this part here is 1, so we get 1 here. This is 0, 0, 0 also, and this one is also 0, so we get 0 because all of them are zeros. 0, this is also 0, but we have here 1, so we get 1. So this one is 0, 0, 0, and 0, so we get 0 here. All right, now let's write our final answer, the simplified one, that is not A plus not C. And then let's see if it is the same with our column F. So we say that this is 1 plus 1, we get 1. 1 plus 0, still we get 1. 1 plus 1, we get 1. And then 1 plus 0, we get 1. And then 0 plus 1, we get 1. And then 0 plus 0, this is 0. And then 0 plus 1, we get 1. and then 0 plus 0, we get 0. Okay, so as you can observe, the column F is the same as the column not A plus not C, which indicates that not A plus not C is the same as these long expressions here. Okay, so let's answer this problem as our last example. So again, we will simplify this using Boolean algebra. So on this problem, you can notice that there are so many negations. In this case, you have to use the De Morgan theorem. It is stated in the De Morgan theorem that we have to work on the most upper part negation. So we have to work on this negation. To do that, we have to break that bar. And after breaking it, it will turn to be. Okay, so the addition here becomes multiplication. The or here becomes an, this part. Okay, then we apply the identity property, which states that double negated A is the same as A itself. So let's apply this to this expression. So this becomes, and this becomes, okay. Then after that, we can apply distributive property here. So let's distribute this expression to each of these terms inside of the parentheses. So this will give us, then we apply the rule that A times A is the same as A. So this becomes A times not B plus, so we have here not B times B. So what is the answer for not B times B? So if we set B to 0, this becomes 1 times 0, the result is 0. If we set B to 1, then this will become 0 times 1, which is also 0. So it doesn't care of the input from B. As long as we have this expression, the answer is always 0. Therefore, this term here is 0, and anything multiplied by 0 will always be 0. So this term here is all zeros. So what we get is just A times not B. So this becomes A times not B. Okay, so let's write down the truth table for this so we can validate our answer if it is correct or not. Okay, so let's check for A multiplied by not B. So 0 times 1, that is 0. 0 times 1 is still 0. 0 times 0, that is 0. 0 times 0 is still 0. 1 times 1, this is 1. 1 times 1, this is 1. 1 times 0, 0. 1 times 0, 0. So our column, A times not B, is the same as the column for our final answer. So let's see the logic circuit for this. Okay, so again, you can clearly see that the non-simplified has too many operations compared to the simplified version.